First, I would like to introduce our group member. First, Siti Aisyah. Second, Sabrina Batrisya. Third, Naimah Husna. Fourth, NURAINSYAFIQAH. And fifth, and lastly, BATRISYIAIRDYNA. For introduction, cloud chamber, a simple yet astonishing experiment done to observe particles. It is cheap and easy to set up, making it a good experiment to be done by students to observe charged particles and interaction. The first part of the cloud chamber experiment that was done is by using a cylindrical container measured 10 cm diameter to observe the particles in it by flashing the inside. And the second part is by using a large cuboid container to observe particles in large area. Both of these are diffusion type cloud chamber.
We will go to the next part, which is a methodology. For the apparatus and materials, there is a transparent container with cap, dry ice packet, isopropanol, which is an alcohol, smartphone, torchlight, fat fabric cloth, and black pepper. For the procedure is, first, a full piece of felt was cut into a circular shape that fits the size of the bottom of the jar. Next, the round shaped felt was placed in the jar at the bottom, and the alcohol was sprayed evenly on the felt and make sure the felt is completely saturated with alcohol. Note, do not overspray with alcohol as this will cause the entire interior of the container to be too humid and affect the result of the experiment. And the container was inverted and closed by the cap. The black pepper was cut in circular shape, equivalent to the cap, and was placed onto the cap. The entire inverted container, where the black pepper at the cap at the bottom and felt at the top, was placed on top of the dry ice slice. Note, make sure the bottom of the cap is evenly cooled by the dry ice. All the lights in the room were switched off, and the phone torchlight provided illumination to the alcohol vapor, and the result were observed and recorded with AI apps called RoboFlow Demo.
Now, let's take a look at the result from our cloud chamber experiment. In our DIY cloud chamber experiment, we observed that the most of time not clear particle tracks were visible. This was likely due to a problem with the setup, like the container was not fully sealed. As a result, alcohol vapor escaped, which reduced the level of supersaturation need for visible track information. Additionally, when track did appear, their visible was inconsistent and short-lasting. This made it difficult to capture clear and reliable results. In this setup, we used a cloud chamber powered by an electric source. During the observation, we clearly saw continuous particle tracks throughout the entire session, unlike the DIY setup. And we also observed that the multiple track types were successfully identified using RoboFlow. In this setup, we used a cloud chamber powered by an electric source. During the observation, we clearly saw continuous particle. Next, we look at the result of our experiment for the DIY cloud chamber without apps. Without using any apps, it's quite difficult for us to detect and observe particles clearly. Next, we look at the result of our experiment for the DIY cloud chamber without apps. Without using any apps, it's quite difficult for us to detect and observe particles clearly. Next, we look at the result. In this experiment, we analyze the different types of particles based on the track they leave in the cloud chamber. First, alpha particle leave thick and short track. This is because they are large, heavy, and highly ionizing, but they don't travel far and low energy. Next, electron, thin, long, and wavy curved track. They are lighter than other particles, so they get scattered more easily. Lastly, for muon, thin and straight track. This is higher energy particle that come from comic ray.
For the discussion part, our experiment using the cloud chamber helped us to observe something we normally can't see, like radiation. Even though it's invisible to human eyes, radiation becomes visible in the chamber through the effect of radioactive decay. There are a few types of radiation involve alpha particles, beta particles, and gamma ray. Alpha particles are made up of 2 proton and 2 neutron. Basically, they are same as a helium nucleus. Because of their large mass and positive charge, they don't travel very far and have low penetration. Beta particles, which are high energy electron, are much smaller and carry a negative charge, so they move faster and further. Gamma ray are completely different. They are electromagnetic wave with no charge or mass, and they are the most penetrating. They can't be directly seen in the chamber, but they might still affect it in the other way. Inside the chamber, we use alcohol vapor to help make this particle visible. The bottom of the chamber is cool, which create a supersaturated layer. Basically, the air holds more vapor than usual and becomes sensitive to any kind of disturbance. So when the charged particle passes through it, it ionizes the gas along its path. The alcohol vapor then condenses around the ionized area, and that's what forms the visible trails or track that we see, kind of like the trails a jet leaves the sky. This track shows us the path of radioactive particle and help us to understand their behavior.
There may be a slight miss at the start of the experiment. Usually, dust particles in the chamber cause this by starting condensation. Once the dust settles, this mist usually goes away. White threads are visible in the chamber as a result of the radiation, but they are transient and vanish quickly after they form. Sometimes there might be fewer threads that are visible. This might happen if the chamber loses its ionization sensitivity. In these situations, applying a glue such as cotton or soap to the chamber top produces static electricity, which can revitalize the interior environment and make the threads visible again. To improve data collection and analysis, this experiment also used contemporary object detection techniques, in addition to the visual observations of particle trails. Using webcam input, we perform real-time object detection using the RoboFlow platform and the YOLO V8 You Only Look Once version 8 algorithm. To detect and follow the visible condensation trails that alpha and beta particles in the cloud chamber leave behind, the YOLO V8 model was trained or modified. We were able to digitally record and categorize particle paths by utilizing computer vision and machine learning, which allow for a more accurate examination of their motion, duration, and frequency of occurrence. In conclusion, the cloud chamber experiment effectively showed that radiation can be identified by the tracks it leaves behind. Even though it is invisible to the human eye, we were able to see the visible trace of alpha and beta particles as they ionize the air inside the chamber by using a supersaturated alcohol vapor environment. These tracks offer a clear visual depiction of radioactive decay as well as the various behaviors of charged particles. Additionally, the experiment demonstrated that the basic actions like cooling the base and producing static electricity can greatly improve the visibility of these tracks. Overall, the chamber demonstrated the value of scientific tools in bringing the invisible facets of physics to light while also expanding our knowledge of how radiation interacts with matter.